All right, well, welcome to our lecture recording for section 7.2. In section 7.1, we were introduced to the topic of parametric equations. Okay, now that we've learned how to represent curves using parametric equations, we're going to talk about how do we do calculus with curves that have been represented parametrically. And specifically, how do we compute derivatives? How do we interpret those derivatives? How do we compute integrals? And of course, we learned how to use integrals for multiple things, and we'll talk about how to adapt them for several different purposes that we've discussed in this course and in the previous course. So, let's go ahead and have a look at our outline. Okay, outline for section 7.2. In this section, we'll explore the calculus of parametric curves. Alright, so we're going to begin by building off of an example we did in the last section where we had a cutting tool in a CNC machine that was cutting a groove from a position that we had marked as 4, 3 to a position marked as 0, 8. Okay, and we had said that the path that's followed by the cutting tool as it makes a straight line between these 2 points can of course be described by a standard linear equation, y equals negative 3/4 x plus 6. We just use some basic things that you would have learned in algebra classes to find the slope of the line and then build it using the template y equals mx plus b. Okay, but then we also found that we could represent that same line using a pair of parametric equations where t in this case represented time, and it allowed us to make both x and y directly dependent on time so that we could control the speed of our cutting tool, which was important in this application. So now let's actually come back and talk about speed a little bit more. First though, I need to get the slope of our cut, and that's best done using our standard equation that had just x and y, because as you learned in Calc 1, the slope of a curve described with x as the horizontal variable and y as the vertical variable is just dy dx, the derivative of y with respect to x. Okay, in this case, this is a fairly straightforward function. It's pretty easy to find its derivative. When I take the derivative of y with respect to x, the first term is just a constant times x, so the derivative of that term is the constant, and the derivative of the second term is a constant, so that's my derivative, but that's also my slope. Okay, that's the slope of our cut as it goes from, let's go ahead and kind of recreate this over here. So where was it? It was at 1, 2, 3, 4, Alright, so it was starting at 4, 3 and coming down to 1, 2, 3, 4, 8, 0. So it would be coming down 3 and over 4. That's a rise of negative 3 and a run of 4. So that's our slope. But now, let's actually talk about our speeds. So in part B of the outline, it says, find the horizontal speed of the cutting tool. Okay, now remember, x is measuring horizontal distance. Speed is the rate of change of distance with respect to time. So if I want the horizontal speed, I need the derivative of x with respect to t, which means I'm going to come up here to my parametric equations where I have an equation that gives me x as a function of t, and I'm going to take the derivative of that to get dx dt. Alright, go ahead and shut that back off so I can see my camera again. Alright, so I had x equals, I already forgot what it was, I gotta look again, 4/5 t plus 4. So now if I take the derivative of x with respect to time, I'm just taking the derivative of this function. So I would again just wind up getting the constant next to the t. Okay, which is what we would expect. Alright, so 4/5. Now remember, we were measuring things in inches. Okay, we're we figured this out last time. If we go down 3 and over 4, we're going 5 inches. Okay, so our speed horizontally is going to be 4/5 of an inch per second. Okay, now remember, we had specifically designed these parametric equations to meet the specification that the speed of the cutting tool as it moves through the aluminum be 1 inch per second. Okay, we haven't actually computed the speed in the direction of movement. We've simply computed the speed in the horizontal. Okay, it's sort of the horizontal component of the speed. Let's go ahead and get the vertical component of the speed. So again, referring back to my parametric equations, the parametric equations in the second equation give me y as a function of time. So I'll jot that down on my paper. Y equals -3/5 t plus 3. That's a 5. And so now that I have a function that gives me y as a function of t, if I take the derivative of that function, I'm computing dy dt, and the derivative of that function is -3/5. Now in this case, the negative tells me that my vertical position is decreasing, and of course it is. Okay, but it tells me also that the absolute speed is 3/5 of an inch per second. Okay. Now, before I go any further, I want to point out a connection that I hope feels fairly logical. Okay, there's a connection between my slope, dy dx, and my horizontal speed, dx dt, and my vertical speed, dy dt. Okay, and it's a connection that I would kind of expect from algebra. I mean, if I take dy dt and I divide it by dx dt, then that would be the same thing as dy dt times, I've got to flip this bottom fraction, so that would be dt dx. But it seems like that ought to cancel the dt's and give me dy dx. Well, let's try it out. Here's dy dt, so that's -3/5, and dx dt was 4/5. Well, let me see. When I flip, I get -3/5 times 5/4, which is -3/4. And if I go back up to the top, -3/4 is dy dx. So that does seem to hold, and it makes sense that it would. Essentially, we just have the dt's canceling. Now in this case, t represented time. T doesn't always represent time in parametric equations. It commonly does, which is why we like to use t for the parameter. But as you've seen, sometimes the parameter is something else, like an angle. And probably the second most common thing to use for the parameter is the theta symbol that we frequently use for angles. But t doesn't have to be time. But honestly, no matter what t is, it's going to cancel out when we take dy dt and divide by dx dt. So that should give us dy dx. Which means that if we're interested in getting slope and we have parametric equations, there's a fairly straightforward way to do it. Okay. Now, if you have a standard equation where y is written as a function of x, it's really easy to get slope. You just take the derivative, because that derivative is dy dx. But sometimes we don't have the standard equation. Okay, we just have the parametric equations, and sometimes we talked about how you could convert the parametric back to the standard. But sometimes either we can't figure out how to do that because the algebra is messy, or we just don't want to mess with it. We want to work with the parametric equations. Okay, and in that case, what we're seeing here is if you want dy dx, if you want that physical slope, you can go ahead and take the derivative of the x equation, the derivative of the y equation, and then divide the y derivative by the x derivative, and it still winds up being dy dx. That's actually going to be our first theorem for this section. So let's actually let's have a look at that real quick before we do part D of this example. So this is theorem 7.1 of section 7.2. I guess there were no theorems in section 7.1. Derivative of parametric equations. So consider a plane curve defined by parametric equations where x and y are both given as functions of t. Suppose that the derivatives of those two equations both exist, and this is kind of important, suppose that the derivative of the x one is not 0. Why? Well, because we're going to divide by it. Alright, then if all that's true, then dy dx, which is the physical slope on the curve, same as it was in Calc 1, I mean x is horizontal distance, y is vertical distance, so we need them to get our slope. Dy dx is just dy dt over dx dt. Okay, pretty straightforward thing to apply, and that's our first calculus equation, or calculus theorem for parametric equations. Alright, one thing I did want to point out before I moved on is we can actually use the horizontal speed and the vertical speed to come up with the speed in the direction of motion. So that was part E. I guess we've already done part D. We discussed that relationship between those derivatives. But part E, find the speed of the cutting tool in the direction of motion. Well, so here's the thing. Our speed in this case could be thought of as a vector quantity. And actually, since we're treating it as a vector, we probably should have called it velocity, but that's alright. We're not doing a very formal treatment of speed and velocity and vectors right here. Okay, but thinking in terms of vectors, dx dt was my horizontal component, and dy dt was my vertical component. Okay, dy dt was going down. Okay, if I want to find the speed that was actually in the direction of movement, I need to find a resultant magnitude from these two components. And I don't really want to spend a lot of time talking about the theory of vectors right now, but this is something that actually came up in one of the homework problems, and I thought it would be nice to touch on because there's actually going to be a lot of time spent on this in Calc 3. Okay, and typically parametric equations will be involved because they allow us to involve time in a nice way. That's supposed to be a dt there. It turns out that if I have the x component of a vector quantity and the y component, then if I want to get the magnitude of that quantity in its direction of movement, I just have to apply the Pythagorean theorem to my components. So I need to take dx dt and square it, and add the square of dy dt, and take the square root of all of that. So let me see, that would be dx dt was 4/5 squared, dy dt was negative 3/5 squared. So that's going to be 16/5 plus 9/5, which makes 25. Well, you know, I was saying that a little wrong, a lot wrong. 16/25 and 9/25. So when I put them together, I get 25 25ths, which of course is 1, and the square root of 1 is 1. That's 1 inch per second. And you might remember we designed our parametric equations specifically with that as a design specification. Okay, there's always multiple ways to parameterize a given curve, but we chose this specific parameterization to make it so that it would take 5 seconds for our cutting tool to go 5 inches. That's what we wanted to happen. We wanted the speed in the direction of movement to be 1 inch per second. Okay, we did that on purpose. This just gives us a nice confirmation that the parametric equations we designed are doing what we wanted to do. Okay, but now let's get back to this. The fact that you can get dy dx from dy dt and dx dt. Alright, so back to the outline. Alright, so it looks like we want to have a look at example 70. So let's pop over and do that. Aha! Here we go. Chung, 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 chung. I guess not example 70, problem 70 from the end of the section. Here we go. What are the instructions? For the following exercises, determine the slope of the tangent line. Alright, so that's dy dx. Okay, then find the equation of the tangent line at the given value of the parameter. Alright, so let me jot this down. X is the square root of t, y is 2t, and t is 4. Okay, so t is 4. Alright, got it. Well, so they asked us to find the slope of the tangent line. That would be dy dx. I can't get that directly from these equations because I don't have the standard equation where y is a function of x, but I can get it indirectly. I can first compute dx dt, the square root of t. Well, let me see, that would be 1/2 t to the negative 1/2, okay, or 1/2 square root t. And then dy dt, well, that one's pretty easy, it's just a 2. And then, according to our theorem, dy dx should be equal to dy dt divided by dx dt. Makes sense. So that would be 2 divided by 1/2 square root t. Well, when I flip this, it's just going to come up here, and it's going to multiply with that 2 and give me a 4 square root t. Okay. Now, notice, usually when we get dy dx from a standard equation, we get dy dx as a function of x. But by building it this way, we got it as a function of t. But I do want to kind of show you something. Okay, we could have gotten it like this. We could have said, hey, if x is the square root of t, square both sides, x squared is t. But then, hey, if x squared is t and y is 2t, well then y must be 2x squared. Okay, we could have combined the parametric equations to get a standard equation. Okay, and then if I take the derivative of that standard equation, that would give me dy dx directly. That would give me 4x. Now keep in mind, x equals square root of t. So these two different formulas for dy dx are really equivalent when you consider that x is equal to the square root of t. They're the same formula, but stated in different ways. As it happens, this way is a little more convenient for us because we weren't given the x value at the point where we want the tangent line. We were given the t value. So we're going to take that t value and plug it into this formula for dy dx. Alright, so I'll just kind of restate it. Dy dx is 4 square root t. So if I want dy dx, the slope, when t equals 4, well, that would be 4 square root 4, or 4 times 2, which is 8. Alright, let's put a little box around that. Okay, that's the slope of our tangent line. The slope of the tangent line is 8. Boom. But that's not all the problem asked us to do. The problem also asked us to find the equation of the tangent line. Now, to find the equation of a line, we can use our little template, y equals mx plus b, and we've got the m, so y equals 8x plus b, and if we can just fill in what b is, we'll have our equation. Now normally we get b by plugging in the coordinates of a known point for x and y. And as it happens, I was not given a known point. However, I was given a value of t. Okay, we're finding the tangent line at the point where t is 4. Now remember, we have formulas that allow us to take t and get x and y. When t is 4, x would be the square root of t, so it's the square root of 4, it's 2. And y is supposed to be 2t, so it's 2 times 4, it's 8. Okay, so this value of the parameter corresponds to the point 2, 8 on the graph, x value, y value. So 2, 8 is the point on the graph where we are finding the tangent line. It's the point where the tangent line is tangent to the curve. So now we have values that we can plug in for b. We can say, alright, 8 for y, 8 equals 8 times 2 for x plus b. So 8 equals 16 plus b. So it looks like negative 8 equals b. Alright, now I can write the equation of my tangent line. Y equals 8x minus 8 is the equation of the tangent line. And that is all there is to that problem. Now, isn't that kind of refreshing? Very straightforward problem, right? I know you guys are all going to nail that one on the next test. And yeah, there'll probably be one like that, because this is a pretty bread and butter problem for Chapter 7. I mean, we're working with parametric curves, and it's a calculus class. It makes sense that kind of a big deal for us would be something like finding a derivative to get a slope on a parametric curve. And I know you guys can do that. You guys have done some very challenging things this term. That right there will be a nice little break when you're working on that one. But of course, there'll be some more challenging stuff too. There always is. Alright, well, let's go back to our outline. Alright, so here's a function. Okay, and we're going to graph this function with Desmos. Okay, so let me just jot this down on my paper here. Y equals 1/2 x minus 4 to the 3. Let's graph this with Desmos. Okie dokie. Alright, so y equals a parenthesis, a 1 slash 2 x minus 4 parenthesis caret 3. Alright. Well, you know, it looks like all the actions are going on over here, so maybe I'll grab this point, and maybe I'll grab I guess I gotta grab the origin and move that. Alright. So, it looks like this is just a fairly basic cubic curve. It's been horizontally shifted and maybe also flattened a little bit. Okay, so there's our function. Now, let's find its derivative. That's going to be part B. Part B, find dy dx, graph it, and discuss what its graph tells us about the slopes of the tangent lines of the original function. Alright. Well, let me see. Since I have y written as a function of x, computing dy dx should be pretty straightforward. I just need to compute a derivative. It looks like I've got a function within a function, so I better remember to use the chain rule. Chain rule says first differentiate the outer part. So bring down the 3, leave the inside alone, knock 1 off the power, but also multiply by the derivative of the inside. Okay, so it looks like my derivative, maybe if I clean that up a little bit, it would be 3 halves times 1/2 x minus 4 squared. Alright, let's put that in Desmos. Alright, so this is going to be our derivative, y equals 3 halves, and then the rest of it's almost the same. So maybe I'll just cut and paste, change that 3 into a 2. Alright, so my derivative is this blue function. Now remember, when we graph the derivative as a function, here I wrote y, but that y is really dy dx over here. So that means these y values on this blue curve should correspond to slopes on this red curve. Now, I notice on the red curve, if I come down here, okay, my curve's going up, so my slope should be positive. So if I go straight up, keep the x value the same, and just go straight up to the blue curve, yes, I have a positive y value. Check, check. But I also notice that as I move to the right, the slope, it's still positive on my red curve, but it's not as steep as it was. So my y value up here on the derivative, while it should still be positive, it shouldn't be as high as it was. Okay, now notice that the slope keeps getting less and less steep until right here. Here, actually, the tangent line would be horizontal. The slope is 0 for just an instant, which corresponds to my blue curve coming down and touching the x-axis right at that point. Okay, but then, of course, as I move on to the right, okay, I can see that my slope starts to increase again, and that corresponds to the y values on the blue curve heading back up in the positive direction. And the higher I go up the red curve, the steeper it is, so my y values continue to climb back up. Alright, so that's the graph of the derivative, and its y values tell us all about the slopes on the original graph. But notice that we have to kind of match up the x values. Okay, so like right here, this is an x value of 6. So if I plug that into the derivative, you know what? How about I call this f of x? Yeah, I like that. And I'll call this one f prime of x. Yeah, it doesn't like that. We'll call it g of x. Okay. Then I can say, hey, what's g of 6? It's 1.5. Okay, so that's telling me that if I come over here to this x value, then the y value of the blue curve is 1.5, and that in turn is telling me that the slope on the red curve at that same x value, okay, an x value of 6, the slope here on the red curve is 1.5. Okay, something that's really important about this relationship is that the x values are matched up. At any given value of x, I plug it into this curve. Okay, if I plug it into this curve, I get the slope from that curve. Okay, but it's showing up as a y value on this curve, but the x's are correlated. Okay, slope for y value. Okay, they make the connection. That's a very important thing to see. Now, let's go back to our outline. What else does our outline call for? Okay, find the second derivative. Okay, so notice the notation for the second derivative is d squared y dx squared. Okay, so find our second derivative, graph it, and discuss what its graph tells us about the concavity of the original function. Okay, well, let's go to the paper for a moment. Since we've already computed the first derivative, we can just take the derivative of the first derivative with respect to x to get the second derivative. And in fact, that's where the notation comes from, because that dy dx, you could understand that as the derivative of y with respect to x. That's dy dx. Now, if you take the derivative of that, that's the derivative of dy dx with respect to x. Okay? That's where they come up with this business of the d is squared, but the y isn't squared. But dx is being multiplied by dx, so the dx is squared. It's meant to be squared as the whole thing is squared, but we don't put parentheses. That's where that stuff comes from. But at any rate, we're going to get there by taking the derivative of dy dx, which means we're going to bring down another 2. That's going to give me just a 3. But we're going to kick out a 1/2, so that's actually going to put it back. So it's still going to be 3/2 times 1/2 x minus 4. Well, that's just a silly looking 1/2. Let's fix that. And now the power is dropped to 1. Okay, so let's graph that. I know I could simplify that, but Desmos will know what I mean. Alright, so the original function was f, the first derivative was g. I guess I'll call the second derivative h. Okay, so 3/2 times basically this part that's in parentheses here. Now, notice that this second derivative, this straight line, is negative. It has negative y values everywhere to the left of 8, but it has positive y values everywhere to the right of 8. Okay, now what does that tell me? Well, the second derivative is the derivative of the first derivative, so it's giving me slopes on the second derivative. Okay, so the fact that the second derivative has a negative y value here, let's say here at x equals 4, the fact that the second derivative has a negative y value corresponds with the fact that the first derivative has a negative slope up here at 4. Okay, likewise, if I come over here to, say, 12, well, there, the second derivative has a positive y value, and that's because the first derivative has a positive slope there. Okay. Now, anywhere the second derivative is increasing, which is actually kind of everywhere here. Okay. Let me say that again. Anywhere that the second derivative is positive, the first derivative has to have a positive slope. Okay, and if the second derivative is positive and increasing, then that means the slope of the first derivative is increasing. Okay? If the slope of the first derivative is increasing, then that means that, so the first derivative is the slope of the original curve. That means that the slope of the original curve is increasing. Okay? Now, if the slope of the original curve is increasing, that causes it to be concave up. Okay? You think of concavity in terms of bowl shapes. The right-hand side of this red curve is like the right-hand side of a bowl that is a right side up bowl. Okay? The right side of this curve is concave up. But notice the left side of our red curve is concave down. That corresponds to the second derivative being negative. Everywhere that my second derivative is negative, my first derivative is decreasing. Okay, and if my first derivative is decreasing, that means that my slope is leveling off on the original curve. And that leveling off of the slope, okay, that leveling off of the slope is what gives it the concave down behavior. So here's what you have to remember. Anywhere that the second derivative is positive above the x-axis, the original function is concave up. But anywhere the second derivative is negative, anywhere it's below the x-axis, the original function is concave down. Okay? This is all stuff that you learned in Calc 1, but I'm reviewing it now because now that we're doing derivatives again with parametric equations, we're going to ask some of the same questions about the behavior of the graph. Now, let's see what else is on our outline. We did part A, we did part B, we did part C. Now, what is part D? We're going to talk about parameterization. We're going to parameterize the standard curve that we started with, and we're going to do it in such a way that t would replace everything that's inside the parentheses. Okay? That'll give me a nice simple equation for y. If t replaces the 1/2 x minus 4, then y will just be t cubed. Okay? So, let's write that down. So, we're going to let t equal 1/2 x minus 4 so that our y, which was originally 1/2 x minus 4 cubed, becomes y equals t cubed. Okay, so I did that on purpose to simplify my y equation, but I still need an x equation. My x equation will have to be consistent with this choice I made here. So I'm going to have to come back here and solve this for x. So move the 4 over, I get t plus 4 equals 1/2 x. Multiply both sides by 2, I get 2t plus 8 equals x. Alright, so if I take this and pair it up with this, I get my parametric equations. X equals 2t plus 8 and y equals t cubed. Alright, let's check that out in Desmos. It should be that if we enter those parametric equations in Desmos, that they'll just cover up that red cubic curve. Alright. So, let's see what happens here. Remember, we enter our parametric equations as a point. So the x-coordinate is 2t plus 8, and then my y-coordinate is t cubed. Alright, well it is covering up my red curve. Okay, but notice it only covered up a portion of my red curve. Okay, and that's because it defaults to having the parameter be 0 to 1. But if I want to get more of the curve, I can just tell Desmos to use a bigger window, like maybe -4 to 4. Yeah. Now that doesn't cover the whole curve either, but it covers everything we can see on this screen. Alright, part D was a success. We successfully parameterized our original standard equation. Let's see what else the outline has in store for us. Part E, construct a set of parametric equations for dy dx and graph them. Well, if I'm going to construct a set of parametric equations for dy dx, then I guess I'm going to need it in terms of t, and I know how to do that. That's what the theorem told me how to do. So let's go back to our piece of paper here. Okay, part E here, our theorem tells us that we can get dy dx by taking dy dt and dividing by dx dt. Well, let me see. Dy dt would be 3t squared, and dx dt would be 2. Oh, well, okay. There's dy dx, okay, as a function of t. But you know what? That's not really enough, because that's just one equation, and I said get a set of parametric equations for dy dx. Okay, now here's something a little bit subtle, but if I want to get a set of parametric equations for dy dx, then I actually have to reuse this x equation. Why? Because when I graph dy dx, dy dx is taking over the role of y. The y values on the graph of dy dx are the slopes on the graph of the original function, but I need the slopes to match up with the points on the original function, and the thing that makes that connection is that the x is the same. So to parameterize dy dx, I reuse my x equation, and I let my dy dx equation replace the y equation. So x equals 2t plus 8, and dy dx is going to be my 3t squared over 2. Now let's go back to Desmos. Now it should be the case when I enter in that parameterization, that should cover up my blue parabola, because my blue parabola was the graph of dy dx originally. You know what? Would it let me call that dy dx? No, it does not like that. Oh well. Too bad. Let's put in our parameterization. Alright, so here's our parameterization for dy dx. This should cover up our blue parabola if we've done it correctly. Okay, x will stay the same, 2t plus 8. But the y, that should be 3t squared divided by 2. Haha! And as you can see, it did cover up a little piece of our blue parabola. And if I expand the domain, I should be able to make it cover up that whole blue parabola. Alright, we have correctly parameterized dy dx. What more could the outline ask of us? You know, it's funny how I talk like the outline is asking things of us. I wrote the outline, but it's because I wouldn't remember everything I wanted to do if I didn't have an outline. Alright, part F. Use the parametric equations from part E to find a formula. Aha! Now we're getting into something a little new here. To find a formula for the second derivative in terms of t, and show that it is algebraically equivalent to the result in part C. Well, alright, so we're going to find the second derivative of y with respect to x. And we're going to do it the same way we always find second derivatives. We're going to do it by taking the derivative of the first derivative. Okay? But the first derivative is stated here with parametric equations, and that's good because the way we take derivatives when we're working with parametric equations is we take the derivative of the y equation and we divide it by the derivative of the x equation. Okay? If I want to take the second derivative, I have to take the derivative of the first derivative, and in the first derivative it's dy dx that is playing the role of the y equation. So that means I have to take the derivative with respect to t of dy dx and divide that by the derivative of x with respect to t. So let me see, if I take the derivative with respect to t of dy dx, I bring down a 2, cancels, I just get a 3t. And then if I take the derivative of x with respect to t, that'll give me just the 2. Okay, so apparently the formula for my second derivative is 3t over 2. Now, keep in mind that when we set up our parameterization, we let t be 1/2 x minus 4. So, if our second derivative is 3/2 t, that should be the same thing as 3/2 times the quantity 1/2 x minus 4, which means that previously when we computed the second derivative directly by just using x's and y's and not involving t at all, we hopefully got that exact same thing. So let's just go back and check. Back up to part C. Aha! Here's where we computed the second derivative the Calc 1 way without any parameters involved. And we did in fact get 3/2 times 1/2 x minus 4. So this form here, this parametric form of the second derivative, is equivalent to the standard form of the second derivative. But I can't translate that into a graph without something for x, because this, the second derivative, will be like the first derivative. It'll play the role of y. My parametric equations equations, I'll use the same x equation that I used for the first derivative and for the original function. Okay, we just keep reusing this guy. X is 2t plus 8. That's what's going to keep everything aligned, so that the slopes and the concavity readings from the first and second derivatives will match up in place horizontally with the original graph. Okay? But the y role here gets taken over by that second derivative. And that's my 3/2 t. Alright. So when I plug this into Desmos, this should cover up the graph of the second derivative from before. So let me see, what was that? Let me see. Here was my second derivative. It was this h. It was this purple line. So when I enter in my parameterization for the second derivative, it should cover up that purple line. Alright, so the x part is 2t plus 8, and the y part is the formula for my second derivative, 3/2 t. Alright, well that's kind of subtle. It made it blue. Maybe I should make it another color. Let's make it orange just to get some contrast. There we go. Okay, now I can see that, yeah, it covered up part of that purple line. Because it's the same line, I just need to expand the domain on the parameter. Alright. Excelente. So, in summary, you get the second derivative of parametric equations the same way you did in Calc 1, by taking the derivative of the first derivative. You just have to keep in mind that for the first derivative, in order to actually graph that thing, you need to bring down the x equation from the original parametric equations, and then repeat what you did to do the first derivative, which is differentiate both parts and divide. Alright, well, I think that's enough to say about derivatives. Let me see, is there anything else on my outline about derivatives? We did part G. I never wrote it on the paper, but we did it. So what we have here is a summary of what we just did. Okay, this would be a good thing to go over. So, summary. To find the second derivative when you have parametric equations, so let's say x equals f of t and y equals g of t. Crud. X and y, f, g, and h are used a little different here than I use them in Desmos. Well, just follow me. To get dy dx, you take dy dt, you divide by dx dt. We'll call that h of t, just so we can say this is whatever it comes at, some formula of t. Then to get parametric equations for that first derivative, we recycle the x equation from the original function, but we let the new equation we just constructed for dy dx replace the y part. Now, if I want to get the second derivative, I just repeat what I did to get the first derivative. I take the derivative of the new y part and divide it by the derivative of the x part. Alright, so it looks like we've got one more example on derivatives, and then we can talk a little bit about integrals with parametric curves. Alright, so let's do number 98 from the book. Looks like I'm going to have to scroll down a little bit. I might have scrolled down too far there. Accidentally overdid it. Scroll back up. Man, this is section 7.3. Good stuff here, but that'll be for the next recording. Alright, I forget what I was doing. 98, is that what it was? Yeah, 98. Alright, find t intervals on which this curve is concave up as well as where it is concave down. Alright, let me just jot that down. We've got x equals 3t squared, and we've got y equals t cubed minus t. Alright, now the problem asked me to find intervals of concavity. To determine concavity, I need a second derivative. To get a second derivative, I must first get a first derivative. So, dy dx equals dy dt over dx dt. Now dy dt, looks like I got to bring down a 3. I get a 3t squared minus 1. For dx dt, I got to bring down a 2, and I get a 6t. Alright, there's my first derivative. Before I can take my second derivative, I need to state my first derivative in full parametric form, though, which means I need to pair it back with the x equation from the original function, and then dy dx is 3t squared minus 1 over 6t. Okay, so dx dt, well, we already said that was 6t. Now for dy dt, notice that we're taking the derivative of a quotient, a fraction, which means we're going to have to use the quotient rule. You might not have thought about that one for a while. For the quotient rule, we take the top and we differentiate it. We multiply that by the bottom, and then we subtract. And when we subtract, this time we're going to take the top and not differentiate it. I'm going to have to kind of squeeze that in. And we multiply by the bottom, and the second time we do differentiate the bottom, and that all goes over the bottom squared. Okay, I'm going to have to simplify that. So the derivative of 3t squared minus 1 is 6t. So it looks like I've got 6t times 6t minus 3t squared minus 1. The derivative of 6t is 6. and that's all divided by 6t squared is 36t squared, like that. Well then, I'll tell you what, one thing I see, that's a term and that's a term. They're separated out by subtraction, but I could pull 6 out of both of those and cancel a 6 against the bottom. So if I pull 6's out, that would give me still a 6t squared minus, alright, I took the 6 out, but I've got a minus 3t squared and a plus 1. The subtraction distributes to the 1. And the bottom is 6t squared. Boy, this is a little problem unto itself, isn't it? Alright, so then we have 6t squared minus 3t squared is 3t squared minus, or plus 1 over 6t squared. Now we can find the second derivative. Okay, that's the derivative of x, and that is, you know, I really wrote the wrong thing here. Let me fix what I wrote here. This is not dy dt. This is the derivative of dy dx with respect to t. But now I can find the second derivative, because the second derivative, so this would be the d squared y over dx squared, that is equal to the derivative of dy dx with respect to t over dx dt. So that would be this thing, 3t squared plus 1 over 6t squared, divided by that thing. That was my dx dt. So it should be 3t squared plus 1 over 36. Oh, there was no square there. That was just a 6t. 36t cubed. There's my second derivative. But that wasn't even the entire problem. The problem is actually to figure out where is this thing concave up and where is it concave down. Okay, that boils down to when is the second derivative positive and when is it negative. So when is the original function concave up? We'll say that's a question. Question. Answer. Answer to that question. When the second derivative, d squared y over dx squared, which is 3t squared plus 1 over 36t cubed, is positive. But when is that? Well, that's actually an easier question to answer than you might think. Check out the numerator. We know that t squared is never negative. No matter what value t takes on, t squared couldn't be any lower than 0. So 3t squared plus 1 couldn't be any lower than 1. The top is always positive, which means the bottom is going to drive this bus. Okay, this fraction is going to be positive if and only if the denominator is positive. But t cubed is positive only when t is positive. If you cube a negative, you get a negative. So it's concave up exactly when t is positive. So the original function is concave up on the interval from 0 to infinity. Notice I'm not including the 0. Okay, the second derivative isn't even defined for t equals 0. Okay, so it's kind of hard to talk about the concavity there. Okay, that it's probably an inflection point. Okay, but the original function is concave up on the interval from 0 to infinity, and concave down on the interval from negative infinity to 0. Okay, basically anytime t is negative, the denominator will be negative. That'll make the second derivative negative. That makes our function concave down. Now, how do I know that I did all that right? Well, let's check it by taking this, the original function stated in parametric form, and plugging that into Desmos. And we should be able to see where it's concave up and where it's not concave up. Alright, well, I don't think we need any of this stuff anymore, so let's just clear this out. Clicky, clicky, clicky. Alright, we want to see what does it look like when x is 3t, I don't know where that came from, 3t squared, and y is t cubed minus t. Now don't forget, it defaults to 0 to 1. Let's do like negative 10 to 10. That should give us a pretty good picture. Well, you know what? Actually, let's do this. Let's let t be 0 to 10, just so we can see the interval, because we found an interval of t values. So here would be positive t values, and yeah, the bowl is up. This is concave up. Now let's look at negative t values. So negative 10 to 0. Aha! On this interval of t values, it's concave down. I would say we did it all correctly. Excellent. Excellent. Alright, well now we can talk about some integrals. So let's do that. Alright, so next example. Use the fundamental theorem of calculus to find the area under the graph of y equals 1/2 x minus 4 to the 3 and above the x-axis from x equals 8 to x equals t to x equals 10. Alright, well, before I actually do that, let's put that graph back up. So we're done with this one. So y equals 1/2 x minus 4 to the 3. Okay, so we're going to integrate this function. We're going to find the area that's under this function and above the x-axis from x equals 8 to x equals 10. So, alright, real small little wedge of area here. We're going to use the fundamental theorem of calculus to compute that. So we're going to take a definite integral from 8 to 10 of 1/2 x minus 4 to the 3 with respect to x. So what I'm doing here is I'm reviewing what you guys learned how to do in Calc 1. Okay, and then we're going to modify this for use with parametric equations. But I want you to see that we're not just coming up with some new formula out of the blue. This formula is really a modification of the setup we're already familiar with to make it work for parametric equations. Okay, so anyway, back to this Calc 1 problem. I need an antiderivative here. So let me see, the power has to increase by 1. So that becomes a 4. And I divide by 4. But I also have to divide by 1/2 because I have to offset the chain rule. If I was differentiating, the chain rule would kick out a 1/2 as a multiplier. And then I need to evaluate that from 8 to 10. So let me see, that's really a 2. So we could put a 1/2 out front. 1/2 times 1/2 x minus 4 to the 4 from 10 to 8. Alright, when I stick 10 in there, 10 over 2 is 5. 5 minus 4 is 1. 1 to the 4 is 1. Times 1/2 is 1/2. Now when I stick 8 in there, oh boy, I picked good numbers for this. 8 over 2 is 4, minus 4 is 0. Alright, so minus 0. So the answer is 1/2. And that looks feasible to me, just from that graph over in Desmos. I mean, what did we have? We had basically a little triangular area, kind of a sunken triangle. But it was a triangle with a base of 2 and a height of about 1. So, yeah, it actually sounds about right that the area would be about a 1/2. Okay, 1/2 base times height. Actually, seems like it'd be a little less, but nope, it is dead on. All right, you have to keep in. Anyway, back to the outline. Alright, so now that we know what the answer should be based on using skills we've learned in the past, we're basically going to redo it parametrically. So we're going to parameterize this function the same way we parameterized it before. We're going to let t replace 1/2 x minus 4, which means that x will be 2t plus 8. And then we're going to find the same area by integrating not with respect to x, but with respect to t. All right. All right, so we did part A of this example. Okay, but now let's do part B. So in part B, we recharacterize our function as x equals 2t plus 8, and then y equals t cubed. Okay, and now if we want to find our area is an integral from what to what? Well, if I want x to go from 8 to 10, then I guess I need to work backwards here. X equals 8 would imply that 8 equals 2t plus 8. So that would be 0 equals 2t and 0 equals t. Okay, so if I'm going to be integrating with respect to t, then instead of having an x value down here, I need to have the t value that corresponds to x equals 8. And let me see, x equals 10 would be 10 equals 2t plus 8. So 2 equals 2t. So 1 equals t. Alright, so I translated my x values to t values. Oh, those are nice t values. Now, let's think about what the other parts of this were. Okay, we don't usually think real hard about this when we set up an integral. But when we're finding an area, remember, we're really finding the area of a bunch of little rectangles. The function gives us the height of the rectangles, and the differential gives us the width, and then height times width gives us area. We're still computing area, so we still want height times width. This time, since we're integrating with respect to t, height comes from the formula for y. So t cubed is going to be my height. Okay, now my width is still dx. And you might say, well, how do I get dx? I get it from here. Okay, since I know that x is 2t plus 8, then that tells me that dx dt is 2. Now if I rearrange that a little bit, then dx equals 2t, 2 dt. So here's the thing. I still really want dx here because dx is my width. But I can't put dx there because I'm integrating with respect to t. So I'm going to put something equivalent to dx. Okay, I'm going to put 2 dt. 2 being the value of dx dt. Now, of course, in this case, that 2 is a constant multiplier, so I can set that outside my integral. I think I'm going to need a little more space here. Let me grab another little piece of paper so that I can finish this problem. So, equals 2 times the integral from 0 to 1 of t cubed dt. And now this is a Calc 1 problem. Yeah, that's 2 times 1/4 t to the 4 evaluated from 1 to 0. When I plug 1 in, I'm going to get 2 times 1/4, which is 1/2, minus 0, and I get an area of 1/2, which is exactly the same thing I got before. So, what do you need to remember from this? Well, basically what you need to remember is that if you're finding area under a parametric curve, instead of f of x dx, it's the formula for y to give you height, and then you replace dx with the derivative of x with respect to t times dt. Okay, that replaces the dx, and then you just integrate normally. This is actually pretty easy. Okay, and I think if we look back at our outline, there's probably a page reference for where this is summarized in the book. Aha, page 633, area under a parametric curve. Let's see if we can find that there. Page 633. There we go. Area under a parametric curve. Okay, theorem 7.2. Oh, I lost it. I gotta be careful clicking on that little bar. There, nope, too far. There it is. Alright, the trick is I gotta hover on the bar and then click the little arrow. Aha! So, what does it say? It says, consider the non-self-intersecting plane curve. Yeah, that would actually kind of mess us up if it doubles back on itself, which is a real possibility with parametric curves. Defined by the parametric equations, blah, 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 x as a function of t, y as a function of t, and t as some interval. And assume that x of t is differentiable. Then the area of the curve is given by, well, y of t is replacing the f of x, and x prime of t dt, that's replacing the dx. Okay, so I mean, yeah, you could just remember this formula, but I think for me, I wouldn't remember this if I wasn't thinking about how do I connect this back to the thing that I'll never forget, which is the fundamental theorem of calculus stated for a standard curve, because I've used it so much, and by this point in time, you have too. Alright, well, maybe we can do some other things with integrals too. Okay, one of the most basic things we used integrals for was finding area under a curve, but we've also used them for computing arc lengths and lateral surface areas, and those formulas can also be manipulated. Okay, let's talk about that a little bit. So remember, for arc lengths, okay, we did this earlier in the term, so I'm going to kind of refer back to what we did. You know, let's say we've got some function and we want to find an arc length from A to B. Okay, and so we divide that interval up into little pieces, And on each little piece, we draw a tangent line. Okay, now those little tangent lines have lengths that are pretty close to being the length of the curve on that interval. They're not dead on, but the idea is that if we take the limit of the sum of the lengths of the tangent lines as the widths of these little subintervals goes to 0, then it would go from being an approximation to being dead on. But then how do we compute them? Well, let's focus on this little length right here. Okay, the width of the interval is dx, and since this is a tangent line, its slope is dy over dx, which means that the rise of my tangent line has to be dy. Okay, so if I kind of blow up this little triangle here, here's my little tangent line segment. Okay, this dimension is dx, this is dy, and this is the length of my little tangent line. Okay, by the Pythagorean theorem, that length should be dx squared plus dy squared, or we can think of those as being in parentheses. Now that's the length of one tangent line, but if I want to take the limit of the sum of all the tangent lines as dx goes to 0, then I just need to stick that into an integral. So my arc length, which we usually call s, would just be the integral of this arc length differential. Okay, where we would let x go from a to b. Now, in this form, I can't really evaluate that very well because I don't have a dx at the end. If I don't have a dx at the end, I can't apply the fundamental theorem, because the fundamental theorem is really designed to compute areas. But if I can algebraically manipulate this to get a dx at the end, then it has the correct form and I can apply the fundamental theorem. So remember, the way I did that was I factored out the dx squared. So I said, hey, this is the same thing as 1 plus dy squared over dx squared times dx squared. Okay, you can see if I multiply the dx squared back through, it would just take us back to here. Okay, but then since I now have a product under a root, I can split the root and take the square root of dx squared, which is dx. And so this becomes the square root of 1 plus dy dx squared dx. Now that right there is the setup that we learned back in chapter 2, I think it was chapter 2. We learned this arc length setup for standard curves, curves where we're just using x and y. But if I want to do arc lengths for parametric curves, I need to modify this setup. To modify it, I'm actually just going to back up to here, and I'm going to do something a little different. Okay, instead of factoring out dx squared, I'm going to factor out dt squared. So remember, when you factor something out, you're really just dividing it out. So if I divide out a dt squared, then I'm going to get a dx dt squared plus a dy dt squared, and then all of that is multiplied by the dt squared. And again, you can see that if I multiply that dt squared back through, it would take me right back to my beginning point for the arc length differential. But I don't want to do that. I want to split that square root and get that dt outside. Now this is something I can work with if I have parametric equations, because when I have parametric equations, I have x as a function of t, so I can compute dx dt. I have y as a function of t, I can compute dy dt. And when I plug those things into the square root, what I get is a function of t, so I would need to integrate with respect to t. Now the only thing I haven't really addressed is that these, by limits of integration, would have to be converted from x values to t values. So let's change them a little bit. Instead of calling them a and b, maybe we call them t0 and t1. Okay, just to make the point that our limits of integration would have to be t values if we're integrating with respect to t. You know, when I say that out loud, that sounds kind of obvious. I don't mean to insult your intelligence. I'm just saying it because I know there's a lot flying around here, and I wanted to remind you. Okay, so let's see if we can apply this to do, I think it was problem 109. What did I say on the outline there? Yep, problem 109. Okie dokie. Maybe I better just roll. If I mess with that scroll bar, I could wind up in chapter 8 or something. Here we go. Problem 109. Alright, I got my x, I got my y, I got my interval. Let's go down here and see what the instructions were. For the following exercises, find the arc length of the curve on the indicated interval of the parameter. Okay, got it. So let me jot that down there. So x is 1/3 t cubed, y is 1/2 t squared, and t goes from 0 to 1. Well, that's kind of nice. I won't have to convert that. They gave me t values. Alright. Now, to apply this formula, it looks like I need to begin by computing some derivatives. So dx dt equals, bring down the 3, just t squared. dy dt equals, bring down the 2, just t. Alright, that's kind of nice. Alright, so my arc length s would be an integral from 0 to 1, because that's my t interval that they gave me, of the square root of t squared squared plus t squared, and then we'll integrate with respect to t. Alright, well, as long as we can figure out how to evaluate that integral, we'll be set. I just took a big drink of tea. I think that'll give me the energy I need to finish this one. At least this problem. Alright, so let me see. That's t to the 4th plus t squared. You know what we could do is we could factor out a t squared. So if I factor out a t squared, that would leave a t squared in the first term and a 1 in the second term. But then I can take the square root of t squared. Now, technically, the square root of t squared could be t or negative t, depending on whether t is positive or negative. Okay? If t is negative, then squaring it gets rid of the negative, and when you take the square root, it's still positive, which means you've negated it. Okay? But, since we're integrating from 0 to 1, we don't have to worry about that. Square root of t squared on this interval, just t. Good, because I didn't want to think about that today. So t times t squared plus 1 dt. Alright, well, so I know we haven't done a lot of integrals for a while, but this is actually a pretty straightforward integral now that I get to this point, because this is clearly something that I can apply u substitution to. I can let u be t squared plus 1 and du be 2t dt. Getting back into integrals is really kind of a almost kind of a blessing in disguise, you might say, because you guys know a lot about integrals. Might be a little rusty, but it'll come back. You've learned a lot. And let me see, I'll move that 2 over. So 1/2 du equals t dt. T dt is what I have, so I'm going to replace that with 1/2 du. Alright. So now I have the square root of u and times 1/2 du. Now, I do have to be a little bit careful here. Since I switched from t to u, these limits of integration have to go from being t values to u values. So if I take t equals 0 and plug it in here, I would get u equals 1. And if I plug in t equals 1, I would get u equals 2. Alright. Now let me see. When I take the antiderivative, that's a power of 1/2. It becomes a power of 3/2. But then I have to divide by 3/2, which is the same as multiplying by 2/3. And there's already a 1/2 in there. Oh, nice. Whack, whack. 2's are gone. Alright. So when I plug in the 2, I get a 1/3 2 to the 3/2 minus, now when I plug in the 1, 1 to the 3/2 is 1, so just 1/3. Alright, well at that point you could plug that into your calculator and get a decimal, which I think is what I'm going to do, because it's like after 5 on a Friday and I think I'm ready to wrap this up. And there's still another example to do. Yep. Let's use the calculator. 1 divided by 3 times 2, no, not minus 2, times 2 to the 3/2 minus 1 divided by 3. That is approximately 0.609 and change. Okay. Did the book give any instructions? Let's check. No, it doesn't say how it wanted the answer. Well, I think that's good enough then. Okay, in MyOpenMath, you'll want to pay attention to whether it wants a decimal or exact form, or does it want a decimal to 5 decimal places, or just read the instructions. Alright, let me see. One last thing to talk about. Finding the arc length of a parametric curve. Oh, we already did that. One more thing though. Just a little further down. Surface area generated by a parametric curve. Alright, there we go. So what did it say? Page 638? That's got to be close to the end of the section. Let's roll up and find it. There it is. Yep, this is it. It didn't put it in a blue box, but here's our formula. Well, you know what? That's actually our formula for when we had a standard curve. Notice the dx at the end. So 1 plus f prime of x is the same thing as dy dx. Okay. This was the formula for a curve revolved around the x-axis. See that down here? So we're taking some curve, we're revolving it around the x-axis, and we're getting the lateral surface area. So not these circles on the ends, just the sides. Okay? But notice that it's basically just 2 pi f of x, which is the height, and then the arc length differential. Well, we already know what the arc length differential looks like for parametric integrals. And if f of x is the height, we know that the height just gets replaced with y of t. So here we go. Here's the formula we want. Okay, this is the formula for setting up a lateral surface area calculation for a parametric curve that has been revolved around the x-axis. It is 2 pi times whatever the y equation is, and then the rest of it, it's the same as an arc length. Okay, so you might want to make a note to yourself. That would be formula 7.6, and what page are we on there? Looks like that was page 638. Alright, well, back to the outline. One last problem to do. I'm feeling pretty stoked about that. Can't believe I just said stoked. What is this, like 1995? Oh well. I was a teenager then, so I think that's a reasonable excuse for using that word. Although I'm pretty sure I didn't use it when I was a teenager. Alright. Find the surface area of the paraboloid generated by taking the graph of x equals 1/2 t squared. I better jot that down. And y equals t from 0, 0 to 1/2, 1, and rotating it around the x-axis. Okay. Well, according to our formula there on page 638, before I can get going, I'm going to need dx dt. That'll just be, well, that won't even be 2t, it'll just be t. And I'm going to need dy dt, which would just be 1. And you know what? Notice it didn't give me an interval of t values. It gave me the points on the curve. So that's x value, y value, x value, y value. So let me see. Well, you know what? Y is actually nicely tied into t. So at this point, since y is 0, t must be 0. And here, since y is 1, t must be 1. Now I could also use this formula to get it, but it's kind of easier to use the y equals t one. Now I'm ready to set up my integral. So I'll use a big S, not a little s, for surface area. I know that's confusing, but that's what we do. Little s for arc length, big S for surface area. 2 pi times an integral from 0 to 1. Now remember, in this one there's a y of t before the square root, but y of t was just t. And then square root of, I've got to take the dx dt and square it, and I've got to take the dy dt and square it. Well, you know what, that's not super creative of me. That's almost exactly, in fact, I think that is exactly the same integral we did a few minutes ago, isn't it? Gosh, can I find my work? I shouldn't throw stuff on the floor like that, should I? Why, yes it is. Just a minute ago, we worked out this very same integral. Integral from 0 to 1 of t times square root of t squared plus 1. And that came out to be this stuff down here. 1/3 times 2 to the 3/2 times 1/3. And it looks like the only difference is that this time it's going to be multiplied by a 2 pi. You know what? I take it back. I'm a genius. So 2 pi times, let's factor out the 1/3 and put it under there. 2 to the 3/2 minus 1. There we go. There's our lateral surface area. Well, that is definitely everything that I wanted to go over for section 7.2. Here's the homework problems from the textbook. So as always, dig into it, run into trouble, let me know. We'll hook up on Zoom, we'll go through it. I am happy to help you. Trust me, this is my favorite part of my job. I would love to be talking to you about math on Zoom. Much more so than going through my inbox. which has been crazy of late. But you guys always come first. Alright, stay safe, everybody. Oh, wait. I almost forgot. There we go. I almost forgot. I always say goodbye by looking you in the eye. So take care and stay safe, my friends. Bye.